So, failure instability is a current-driven instability. You have magnetic fields which are not current-free, and if they get strong enough, they get unstable. It's usually a strong field instability, different from the MRI, which is a weak field instability. This is maybe an easy way to define it. If you compare the L-plane frequency of the magnetic field with the angular velocity, and if this is larger than the angular velocity, you may get instability. And I've plotted this as a very simple sketch of what would happen in the sun, for example. So you see in the background, you see the differential rotation. So we know omega at every place in the sun in just a simple sketch. And adding the density profile of the sun, we can look for which fields are unstable where. This is a very simple thing, perhaps for toroidal fields or so. But it gives you an impression about the quantities we are speaking about, and these are numbers like 2 times 10 to the 5, and they're getting a bit larger here inside. But this is only one criterion. You can also get instability for lower fields, but then the growth rates are longer. Well, the growth rates for this case are very, very short rotations.
So the answer to Sasha's question was the answer that Günther gave already a few days ago. So if the angular velocity, or if the Albion speed exceeds the angular velocity, then that is what is meant by strong.
Yeah. Short time field. All of
without turbulence. Right?
Excuse me?
Is it true that it's without turbulent diffusion and turbulent viscosity? All this.
In this case, yes. But you could think of a turbulent domain also and ask for the limits on a large scale for these fields. That's true.
Then you have to have the right equation.
But I haven't done this in this
Then they have to use the right equations.
Right, it's another story.
Yeah. So I don't care about this in this form.
Yeah, the surface density is 10 to the minus 4 centimeter cube. What's the relative magnetic field there?
This could be fairly low then, yeah.
Well, then any field is unstable. I mean, for the
Yeah, probably. I mean, unless the turbulence gives you additional effects which I can't overlook now.
well, you can see that here is not turbulent.
Oh, right.
No, but wait. Well, how much is the Albion speed? It's not so easily above 2 kilometers per second. That's what he's saying. Are you? Sasha? Yeah.
But I mean, the fields are also much
But
lower.
wait, if you have a sunspot,
kilogauss.
the strong.
Consider kilogauss field, and if you can calculate kilogauss field and minus 6.
Yeah, that was unstable, of course, yes, but not anything below that.
So how we see this?
I don't know. I've checked what the field limits would be.
Let's wait until you will come to this, of course, but the manifestation is. You will address this question.
Inside, yeah.
The physical sense of this.
Yeah, you will see what happens inside, and then we can think about what happens outside. Right. So just to give you a sketch of the initial state of the instability, you have a toroidal field inside the star. And as the instability grows, we are concerned here with non-axisymmetric instabilities. You get certain m=1 patterns in the azimuthal field, and then later evolution will be nonlinear and involve other m modes and stuff like this. But the easiest thing is to just look for a stability limit for the m=1 mode, which is in most cases the most easily excited one.
What was the question?
What is the physical sense?
You mean how it works? Right.
Yeah, we know that, say, the connections that different buoyancy,
Yeah. I must say I don't have a good answer for that. Do you want to draw a picture? What's the unstable term? Or
Yeah, no, we should, if I put, some ball on top of the mountain, it's unstable, this, what's here.
I don't have a picture at hand.
Oh, but, so the question was, what is the physical meaning of this? And isn't something like the sausage instability one of the standard pictures?
It's non-axisymmetric.
Yeah, and so it's sausage. Sorry, it's the kink instability, yes. Right? Would that address your question?
Yeah, you want to see a term or so.
So what
Not
the
being
thing
balanced.
that Hank often draws is he has these rings which are getting out of
Yes.
place. And that's exactly
So what
Yeah, but
happens?
this
So
is
it's
no physics.
it's centrifugal force, or what causes instability? What kind
No, it's not the
of-
same.
If it's not kinetic,
It's even unstable. It's
magnetic
non-rotating
tension, because,
case.
you know, something acts against the
I mean,
magnetic tension.
it's this one here.
The kink is, you know, something like
The
this.
kinks.
You know, the-
Yes, that's what it is. How do you call it?
If it's the initial field that is symmetrical, then what kind of magnetic motion is it? You need to know first, you know, to push it up, and that would be, you know, against magnetic tension. Magnetic tension will return it back.
I mean, we are talking about the kink instability. You're not addressing that the kink instability that doesn't make sense. You're not saying that, are you?
No, I think it's not, it doesn't work here.
Yes, it is the king.
It's kink instability.
In MHD, not in blood
Okay,
vessels.
do you think you will address this question, why it is actually the kink instability? No. But then we will,
So let's go Taylor.
then we probably need to postpone this question.
It's Taylor, not Taylor.
Huh?
Taylor was
Yeah, yeah.
Taylor.
Yeah, this is an invention, of course, that was done.
Tokamak, something like
Tokamak, it might be.
That could be, yeah.
So maybe you continue then.
Isn't the kink instability on the picture? On the
In principle, yes.
Yes.
Yeah. Exactly, and this is the very simplest case you can imagine. It's just a toroidal field. There's no rotation, no net rotation, of course.
Google is only Rüdiger, you know, Taylor instability. All you know, the first reference is to Rüdiger, so that he must know what instability is. But nobody else calls it Taylor instability.
It is still called Taylor.
But the printer was the person who invented this name, right? Was it not you?
No.
It wasn't you? It was Sprout maybe, yeah?
Now it is an instability which mainly works in latetive
Yeah,
solid
I understand.
stars.
But who, and of course,
So,
Roger Taylor.
but nobody was interested
No,
over
Roger
decades.
Taylor worked on this, of course, and so did others.
Yeah, and I found out that also Wanda Kulov at the
Yes,
same time
Exactly.
made such a paper.
And what I was only referring to was that you coined the term.
Yeah.
Yes, that's what it meant.
So I called it Taylor Wanda Kulov Institute.
Exactly, yes.
But
So therefore,
nobody
Sasha
followed me, so that it is now again the Taylor Institute.
It was Leonid who prevented you. But
Anyway, I don't know the name.
Yeah, whatever.
I just want to see what happens. So one of the motivations is AP stars, because they have these complex fields. We have seen this graph already earlier this week. And one idea could be you have an AP star forming, and in the early star formation phase it will have braking on the surface, so it will rotate differentially. And any magnetic field will be wound up in the interior. And if this wound up toroidal magnetic field inside reaches a critical limit, it may get unstable. And colloidal fields or surface fields may pop up on the surface. That's what you see as an AP star. The good thing about the Taylor instability is it is called strong fields. So also what you see here on the surface is probably still a relatively strong field, which could resemble the fields observed.
How that's consistent with observations that show that magnetic field can be stars concentrated and peculiar transports with different condition.
Yeah?
Exactly. So
That's
how-
what I expect. What are you...
Because you know the magnetic field concentrates in star spots of different chemical composition.
Yeah. I think the chemical distribution is a secondary effect then of the fields.
Yeah, but it's concentrated there. It's not kind of particular spots.
Yeah, it could happen. I mean,
It's not a toroidal field, like
no, of course, that's what I'm saying. I'm saying that the toroidal field is inside, and you have instability, and this field produces non-toroidal fields, which peak out of the surface at certain positions. You don't see anything of the toroidal field, of course, here on the surface.
We heard, that this is from Pistonov, that this is a model field,
Right,
related field.
exactly.
Stabilities.
Yes, but still you have to think about a lot of things if you want to create such a field from a primordial field, which will be a fairly homogeneous thing. I will come to that in later transparency. Just to tell you something about the characteristics of the Taylor instability. It is affected by rotation that exists for non-rotating case. Rotation stabilizes the fields, and differential rotation stabilizes it even more. So this is a recent graph by Günther and Leonid, which shows that if you have no differential rotation, then the limit is something like this. But if you add differential rotation of whatever sign, the stability limit rises from here to some much larger value. In this case, factor of 10 or so. Oh, it's a percentage probably.
Huh?
It's percentage probably, 10% differential rotation.
Get you something in front of the sign squared or?
Differential rotation stabilizes non-axisymmetric models. That's the message. The numbers are totally irrelevant. Critical field means the critical toroidal field you have inside when it gets unstable.
So here you can see the two cases. One pulse rotates slow and faster, right?
Yes,
So there is
exactly. So it doesn't matter in which direction you go, in both cases it's stabilized.
I have a question. Normally for the kink instability, it's the pitch angle which matters. That is the Anstellwinkel, or whatever you call it.
It's
So,
only toroidal field here.
That is not
It's only toroidal.
Right. So you have just a toroidal field, you add a small perturbation and you get instability or not. Right, this is without colloidal field.
yeah.
Colloidal field will come into play if we ever reach that point. No, we reached it already. So now I take the spherical shell and simulate this in a more stellar environment, let's say. So we have a 3D domain here. This is a vertical cut, and this is what I assumed as a simplified angular velocity in the beginning. The colors are not very clever here because this means fastest and this means slowest, actually. So you assume some braking through disks or whatever in the initial stellar phase, and you usually get such a negative differential rotation. That's what you would expect. And then I put in a colloidal magnetic field like this. Perhaps you can see the arrows. So this is just a colloidal field. And then together with the angular velocity, you wind up typical toroidal field belts. The special thing about this is that this is a consistent computation to here, which means that the upcoming BR, B5 also gives a Lorentz force on the differential rotation. So at the same time when this builds up, differential rotation is quenched. So it's a consistent picture of angular velocity and magnetic field. And then you get a graph like this. So this is the time, and we have the magnetic field strength here. And so we wind up the toroidal magnetic field from 0, so we have just started from a colloidal magnetic field. And you reach a certain maximum, but you can't do this very long because at the same time the differential rotation is quenched and the amplification reaches some maximum. And then, since I have not imposed anything, it's all an initial value problem, everything decays in the end. This is of course a process which will take a very long time in the start, but doesn't take very long in numerical simulations because the diffusion is much larger.
Maybe better calling it breaking instead of quenching, because quenching suggests that it's being maintained by something else, and at the same time.
Okay, well I would rather, I don't like to call it breaking because it's a redistribution of angular momentum. The angular momentum is conserved in this computation. So it's a reduction of the differential rotation.
Decay.
Differential rotation decay, or
Decay.
right.
Okay, yeah, equilibrium.
Yeah. So, and this computation was entirely axisymmetric in the beginning, just to see how this evolves, how far we get with the D5. And now you could say, okay, let's pull out our old stability analyses of the toroidal field and take one of these snapshots and look for the stability limit. Is the field actually already above the stability limit for an m = 1 case, or not? And then you see that with this case, you reach the stability limit, because this is the stability limit for any of these configurations as a snapshot. So the whole star would not get beyond this point, because it would get unstable. So this was m equals 0, that's why we don't see the instability here. And if you add the m equal 1 stability analysis, you get this limiting line. Okay, that's maybe also not so exciting. We want to see how that looks in a nonlinear case. And this is what I've done then. So the whole thing is now, we have the initial problem, the same initial problem with differential rotation and colloidal magnetic field. You let it wind up, but you compute all the additional modes, I don't know, 20 up to m equals 20 or so. It was a moderate resolution in m. And you let it evolve, and then you should see, if you put in your perturbation at some point, this is what I did here, at 0.002, this was actually, oh, it's a different time scale here, unfortunately. But it was somewhere where the field was reasonably large already. You put in your perturbation, and then you see m equal 1 things growing. These, the dashed lines, are the m equal 1 contributions. This is the old curve of amplifying the magnetic field and then some decay. And here you see that the m equal 1 magnetic energy at some point dominates the regime. So this is what I would call the nonlinear evolution of the Taylor instability in 3D.
Can you extract an exponential growth at intermediate times? Have you seen that yourself? You don't see it here.
Yeah, you don't see it here, yeah. It's
But you have seen
probably
it.
too much immediate back reaction on everything.
Yeah.
There's no real kinematic thing in quotation marks. It's a magnetic instability, it's not really. Right. I think there's also some sketch of how it looks. There are a couple of snapshots which I've put here in an animated GIF, where you see the m equal 1 thing growing up. Yeah, it's not telling too much, just to give a rough impression of how it looks. There's a lot of field coming up at the pole, actually, which may be interesting for other things or for comparisons with observations. Right, and now the big question is, can this m equal 1 instability couple nonlinearly to the other m modes in a way that you derive an axisymmetric alpha effect? It is in principle possible. It may be there, but it may not be there. And the idea was actually motivated by Henk Spott's idea that this could drive a dynamo. And then, of course, or one indication would be if you find such an alpha, then this could be the basis for a dynamo. Still, it may not be a dynamo because the alpha may be too small, but looking for an alpha is the natural thing. So this is, of course, a very simple thing I did here. So this is just assuming you have that alpha phi phi is the main contributor to this. And I computed it just from the velocity fluctuations and magnetic field fluctuations, averaged them over phi, and compared it with the average b phi averaged over phi. And then the whole thing is averaged over beta and r in hemispheres. Right?
You do it as a scalar type, perhaps, yeah?
And one is this the southern hemisphere, the diamonds, and this is the northern hemisphere, the asterisks. And this is just the time, and I've just taken my 3D snapshots I had available and extracted this information.
The average then with all the rest also, yeah. So I can see.
For the half hemisphere, yeah.
So at the northern hemisphere, the second part is negative.
Yeah, most of the time it is negative. It's just this excursion where something vigorous was going on.
Yeah. It's the same result as we obtained for the linear circle with Leonid. The northern part is negative and the southern
For the Taylor instability?
Yeah.
Oh, okay.
I should. I
And this-
concentrated to the poles.
This was the time where I had imposed the non-axisymmetric perturbation, so this is not the time when this whole thing starts to appear. And the question is this really the Taylor instability which produces the alpha effect? And this is why I have done the same computation, but have imposed the non-axisymmetric perturbation here, right at the beginning. And so if this alpha which we see is just an effect of the decaying perturbation, then we would see an alpha effect in both cases. So here you see the same evolution as 2 slides before. but you see that the m=1 modes never dominate the thing. You just see the amplification of the field here and then decay. So this perturbation doesn't appear to get Taylor unstable, as expected, because we haven't wound up the toroidal field yet. So how does the alpha effect look like in this case? It is 0. It is quite convincing that the alpha effect was indeed produced by the Taylor instability. And that's the main result of this computations. And now I come back to the question by Sasha about the fossil fields originally. There is a parallel work which I'm doing, is that you assume that in the protostar phase you have a short convective phase, and this will process your fossil fields. And this is what I've done in relatively large simulations here, to really have an evolution of the convection, actually, where you go over time and you plot your radius of the convection zone, your bottom radius. So this would be 1, it's 0. Then you have a typical curve like this from stellar models when the radiated core clears up, and this is convection. So the bottom radius of the convection zone just goes outside, and then it goes almost to this will be a very shallow thing then in the end. And you ask yourself, what is done here during this convective phase to the fossil field? And then at the end, when everything is radiative, you can have a look which sort of, or which field topologies are left over after this convective phase to be the actual AP star fields, which are either seen or subject to Taylor instability. But that's, of course, another talk, in fact. I just want to mention that there may be, of course, the connection between the two, because the fields left over from this short convective phase, so the fossil fields processed in this convective phase, you may plug into our nonlinear evolution with the Taylor instability and see how these fields will actually pop up on the surface.
So actually do computations of pre-main sequence models? Or
yeah, it's of course simplified.
Also that,
yes, but it's of course simplified to just a Gaussian-esque sphere, because if I have a lot of physics, then I can't really cover evolutionary timescales. So it is, of course, it's sketchy, but it may tell you something about the processing of the fields.
From star formation, right?
No, I don't have the collapse inside. It is probably really complicated now.
So what's the initial conditions?
The initial condition is that I have a star. I just put a homogeneous magnetic field in there, so as to mimic an ambient magnetic field. And I also impose a differential rotation on the surface as to mimic some coupling with a disk or so. And then I just let it run. And with convection, of course, I have to put a little hole in the middle for numerical reasons. So I have a Rayleigh number of, I think, 10 to the 8 or so. And yeah, and this then just convectively stirs the whole thing up. I just impose it here on the surface as a boundary condition, actually. Yeah. So this is, of course, a simplified thing.
So that leads to angular momentum transport then, yeah? Out of the sphere.
Well, no, it doesn't lead to that, but what I would need is that also the rotation period would increase over time. I don't have that in, but that could also be done. I don't know if it would change really much the results, that you have the real slow down of the star. I just assume that there's a continuous shear at the surface. That's all I'm doing, which is more or less plausible, I would say.
You're doing three-dimensional calculation.
That's fully three-dimensional.
So convection.
It's full sphere convection, and then it's very good shadow convection.
So then you should get automatically differential rotation, right?
In principle, yes, but in these simulations, no, I don't think I get it because I don't have a density stratification. I think it's
in
very hard.
effect equilibrium or
For the rotation? Yeah, I did.
when you have effect equilibrium, it must be some density direction, right? How to maintain effect equilibrium? It's constant density. You have constant density, right?
Yes. What are you having in mind?
I mean, it's an incompressible star.
Yeah. Yes. It's an incompressible thing, and also the sphere doesn't change shape. So
But it's still
all your pressure is
unstable,
always
right? You
balanced
still
by the
have,
shape.
Regular Taylor instability, right?
Excuse me? The tape?
If you have gravity, constant
Yes.
density,
Yeah.
you have regular Taylor instability.
Yes, you really see convective motions
Yeah.
in there.
And the
So you will have a collapse.
No.
Regular Taylor instability.
Why should it collapse? I mean, it can't collapse, of course, in this model, but why should it?
So you could try using a polytrope or something to go.
No. I mean, the
So he has
pressure
any
here is
compressible
elastic.
calculation.
Yes.
Density is constant.
You can do it in elastic, you know.
Yeah, of course,
Difference.
Right.
Maybe
I
you
mean,
can
of
give
course,
an
the
X
ideal
stop
thing
then.
would be to
More
have it
realistic.
more realistic, but then you will cover much smaller timescales when you do more physics. That's a bit of a
I
problem.
mean, by the way,
In an elastic.
raceways calculations were of course compressible.
Yes,
Compressible,
they
yeah.
were compressible, but they were not rotating.
Because then you wonder what the meaning of these calculations, you know. What try to learn here?
We want to learn if you have a convective processing of a magnetic field
Not rotating.
and rotation, convective rotation, and the convection zone then remains at the end at some small thing. What sort of fields are left over here in the middle? What can I expect if I have all this convective diffusion? Do I expect any fields inside at all? This is of course the main question. And, or it is the same question, does the fossil field theory hold if you diffuse all this by a turbulent diffusion for a while? And the result is there is a field remaining inside, which is of the same order of magnitude as the put in, even if it's stronger.
This of course depends on density classification. This parameter what you showed in the beginning.
No,
No, this is not about the Taylor instability. We're just talking about convective processing of any field. This is not Taylor unstable. These are two talks.
I know, but you know, the convection of magnetic field depends on, you know, how much energy you have in magnetic field, how much energy you have in convection. If you have high density,
It's not
then you know that
that's convection.
it will destroy a lot of quicker magnetic field. It's like in the sun, when in the atmosphere you can see these loops,
Right.
magnetic
Right.
field. If you go down, you know, everything is destroyed by convection. Because density is high, right? Because the convective energy is much higher than magnetic energy.
Yeah, I see your
If you
point.
do the
Of
density
course,
stratification would be the same effect, so that
density
without this is,
stratification would be nice here, but this is a sort of first indication of what happens.
it's
to
a
these
dynamic
fields.
process.
If you think it's not worth anything, then I can only ask you to do it then.
First of all, if you don't have rotation, you have a colloidal field and that's always unstable. And that is what is called the Taylor instability. Isn't that correct, first of all?
Yeah,
Not
that was
all- not always.
my talk was about.
What?
That was what my talk was about.
Yes.
And
And
then
the
the
same
question
is
is,
true for, that was the Claus-Wundermann instability, of course, for the colloidal field. We have, for non-rotating stars, you have the Claus-Wundermann instability for a purely colloidal field. You have the Taylor, or the other instability for a purely toroidal field. Now if you do have rotation, at least the one with colloidal fields gets stabilized, or both. Do both get stabilized? Both get stabilized, yes. And what exactly is called Taylor? I thought that Taylor was already the...
Only toroid.
Yes, and with or without rotation? With or without rotation?
Both.
Yes.
They
So he
stabilize them.
studied, yes, and he studied both with rotation.
In the early Taylor papers, there's no rotation.
Yes, right.
Then there was number 3 or number 4 with
Yes.
some pit or grid,
Yes,
and then they included rotation and found out that the rotation stabilizes.
yes.
So that's why I was the referee of the last paper by Braithwaite in monthly notices. We worked on without any rotation. And my
Yes.
argument, a fair argument, as I believe, was all the stars are rotating rather fast. And you will not find, or there are only a few exceptions, where instability calculations without rotation can be applied.
Yes.
And now in this paper he wrote, indeed, there are 2 exceptions for which this theory can be applied. This is very slowly rotating AP stars, 1,000 years. There are some, or 1,000 days? 1,000 days. 1,000 days, not years. There are some. And magnetars. magnetars have 10 to 15 Gauss, and this is enough so that the magnetic energy dominates the rotation energy. So two applications. But here we are in the area or in the regime where the rotation of the star dominates.
Yes.
The normal AP stars, the normal neutrons.
Yes. I mean, the answer to Sasha is therefore everything which is not known and connected with this and extending previous series is of interest.
It should be called Vanderkurov instability because it's really what.
Excuse me?
It should be called Vanderkurov instability.
I have nothing against it.
Yeah,
But
that's
Taylor
what
was,
they're called.
did something
but
different.
Taylor was at the
The
same time.
rotation is exactly like Vanderkurov.
Yes. Yes.
Yeah.
72 paper.
Hmm.
Which is very nice. He derived a dispersion relation from dispersion relation. You can
Yeah, but
understand the
it's
physics.
not easy to understand.
What do you mean?
I
When
read
you
it
arrive at
several
the
times.
equations and you calculate dispersion relation,
Any comment from good? Because
because
good,
you
of course,
should
will talk about this.
stability analysis.
You don't want to do that? You don't want to give a comment on that? Because
About
on why it's not called Vanderkurov. You know more about
the
it.
first paper by Taylor was 5 years earlier, but in a very exotic publication. So
Taylor.
73.
But without rotation, right?
70 what?
73.
Was Taylor.
No, earlier, 60. I have it. I have it in the paper. So
Okay.
and this is. I would also say that it is at the same time independent of each other.
Yes.
And there is a remark of Taylor in some paper that he got a preprint by Vanderkurov and very similar results, but of course his results are more important. This was very
Yeah.
You know, Taylor did this for parallel flows, that was Vanderkurov reference. But before this was Cherepovnikov. 1960, of course. And Taylor did 61.
okay. You must read my research.
Cherepovnikov.
Yeah. No, that's by the way, of course, common property of any type of research.
Yeah.
It's never so that somebody did something for the very first time and nobody ever thought anything even remotely related. That's never the case.
So Vanderkurov.
So,
Okay, so let's continue then with Meiner's talk. We're continuing, yeah?
No, I'm actually done.
You're done.
What was the outlook? Yeah, I told you the outlook already that one may combine the two things actually with taking fields from simulations and plug them into the activity energy. All right. Yeah, that's it.
So to summarize, I mean, you summarized already.
I summarized already. The main point was, of course, the indication for an alpha effect.
Yes.
And what one could do perhaps better is to look for other components like this, and I don't know, maybe for ether components also. But I haven't done this, and this is something we could probably do by the test field method.
Is there a comment that anybody wants to make regarding what Brian has said so far?
Yeah, I have a comment.
Yeah.
The idea behind this is, or my personal motivation is to check is it possible to explain the AP star magnetism. We had already the discussion about the collapse, and all the collapse calculations lead to the result that there is from the beginning on in the protostar a strong differential rotation. If the poloidal field survives the collapse, why not? Then the star produces over a long time a strong toroidal field. It is unavoidable. And only this strong toroidal field gives the motivation to think about the Taylor instability. Without a strong toroidal field, it makes no sense. And as Rainer showed, nevertheless, this toroidal magnetic field, together with the fossil poloidal field, will quench or will work against the differential rotation. And if one computes the Alfvén time scale for a fossil field of, say, 10 to minus 4 Gauss, then it is 10 million years. That's exactly the time when the AP stars start to exist. This is the old Potsdam result that the AP stars, there are only a very small number of very young AP stars in young clusters. The majority of the AP stars only appears after 30% of the lifetime of an A star. So this is exactly the Alfvén time when the Maxwell stress destroyed the differential rotation. And remember, the differential rotation stabilizes the Taylor instability. That means if after 10 million years the differential rotation does no longer exist, then there is a strong toroidal field and the Taylor instability can work. And this is an idea to explain why AP stars are unstable stars. This is a data. Of course, this is not toroidal field, but this Taylor instability has also poloidal components. And this is what we observe, a non-axisymmetric m equal 1. I still believe that there is a m equal 1. If you are sure that it is not true that AP stars have a dominating non-axisymmetric m equal 1 magnetic structure, then we have more problems.
Yes. And Potsdam result means Krause and somebody
No,
else.
von Oetken, Mrs.
Or,
Oetken. 10 million or 20 million. It is published in one of the latest.
70, yeah?
Yeah, it's published now in one of the latest papers by Svetlana. There is the limit is given 20 million years.
Yeah.
I think the problem here with this logic is that differential rotation to maintain it, you need convection. We know from the sun, from solar observations, the differential rotation exists only when you have convection. You need to maintain.
No, it's an initial condition for the collapse. The sun, this is quite another situation. It is angular momentum transport by convection.
Nathan had a question?
Yes. How this result is sensitive to diffusivity and viscosity? Hard to believe that AP star, totally free from any turbulent or quasi-turbulent motion. If it's true, you should get some kind of effective parameters, which of course larger than the molecular model. It's behind my question.
Nothing against it.
Right. Do you know the answer? How does the instability behave in magnetic resonance number?
Yeah, of course, because the computations are made with small Prandtl number and are made with a very small magnetic Prandtl number and an even smaller normal Prandtl number.
You mean linear or non-linear?
Linear.
Linear.
Yeah.
Because non-linear it's very difficult.
He has not. We have the better job.
Okay. You mean?
We are old enough to concentrate to linear.
Yes, it's correct. You mean not bad, correct? Maybe, but who knows? But correct, yes, I agree.
Any other question? We need the young generation for the nonlinearity.
Yeah.
So you don't have anything, then we should switch.
I have
Yeah.
a small question about start of your population. In first you run 3D case without magnetic field.
No, the first one is a 3D, is a axisymmetric case. That's the difference.
I asked it because if you running with convection from this initial condition, you should.
No, this is not convection. Maybe I should not have mentioned my convection simulations because
Ah,
I will
you
mix
will
them
not
up.
you will not convection.
I confused you entirely. So this is no convection. This is just a radiated thing. You have a colloidal field. You wind it up in differential rotation, which is from the birth somehow. It's not connected differential rotation. And then you look when it gets unstable.
So in your simulation you have not connection.
In this talk, no.
What means?
The convection.
This talk, I asked
this
you
talk.
about
And the connection comes into play when you ask, this is an arbitrarily invented field as a star field.
Yes,
But when you ask yourself, what could be a real field stemming from the birth of the star? Then I did the second story, where I did convection and looked into what sort of fields are left over by convection. And then it will be a future thing to test these fields in this scenario.
And that's where.
Or maybe you just run the computation.
That's how your last sketch was motivated. You just, as a function of time, made the convection zone thinner and thinner. Yeah.
So this is talk 1, and this is talk 2. Makes sense.
So how do you explain that we don't see such things on the sun? Our sun escapes this instability.
It's rotating faster.
Oh, we do see it. I mean, we don't see it, but in the same sense, we are arguing, of course, in the same sense, we are arguing that the toroidal fields you have in the tachocline, in the stably stratified part, that they cannot reach 100,000 Gauss, because they would get Taylor unstable, according to these computations.
No, I mean, so in terms of star formation, just the sun was unlucky not to have enough strong enough primordial field to work.
No, this thing actually will also hold for the sun, and you could say that these fields left behind, and so this goes only to 0.7 here, of course, right? So this will stay convective, and the field left behind inside could be exactly the fossil field, which now produces the tachocline. But you need to do, of course, more things. You need to confine the field finally inside the star. So this is not a direct link, but it could also be interesting for the sun, for the fossil field and the radiative part of the sun.
That's why the sun is rotating rigidly inside.
You see what I have in mind?
I'm just confused about the relation between the first part and this part. I suppose there are some links between these, or totally different.
Well, the link would be...
It's the same piece. The relevance, one relevance is very different when the sun is rotating rigidly in the interior.
Expecting stability. Why the sun is that some less than Gauss,
Some less than Gauss.
What do you mean? Why do you say less than a Gauss?
and this is
I don't get the question.
so why could have 100,000 Gauss and this is the sun.
Yeah, can you write down 100,000 Gauss corresponds to what Alvin speed in that depth?
I assume that that star
Oh, well,
formation
we
is
need to
roughly the
answer.
same.
No, well, in the sun, this would be at depth of tachocline, this would be roughly the rotation speed, right?
Yes, and then it becomes unstable, of course. That's what you said.
But this,
No,
will be,
it's
this,
just a
this becomes unstable even before, at a much slower...
100,000 Gauss.
If this idea of
1,000.
magnetic confinement of tachocline with magnetic field strength is 10 to the minus 4, 10 to the minus 3 Gauss.
Right, I mean, so for the sun, the thing which you find inside here can be very, very small for the sun. And
Yes,
will be
yes,
sufficient.
it must be small.
Yeah, that's the question. If it must be small, maybe this, if this really gets unstable before, then it will turn into something small after some time. We don't know.
We must understand that.
100,000 Gauss.
We must understand that the 100,000 Gauss are excluded, or to exclude is trivial. Then this Taylor condition is violated and it must be unstable. But in a more careful analysis, taking into account the radiation, or the thermal diffusion, the viscosity and the diffusivity of the magnetic diffusivity, the result is that already 1,000 Gauss become unstable.
Something like this, maybe. It's not a one-to-one relationship.
Yeah.
Just to give an impression that it gets
Lower
slower.
radiative interior.
This is for dipoles.
Yeah.
The problem is complicated as it is a current instability. And for example, in the quadrupolar field geometry, the current system is quite different from a dipole. So we get, in the calculation, we get strong differences of this instability for quadrupole field geometries where the maximum of the magnetic field is at the equator. You have one current along the south pole and south-north direction. But for a dipole you have a much more complicated current system. So that's why all the experiments, for example, mimic only a quadrupole contribution. And all the old results of Taylor and so on are only applicable in stellar physics for quadrupole geometry.
Oh, I see.
A dipole is much more complicated,
Fortunately or unfortunately.
I'm still trying to understand, this what.
Yeah, I think I know what you mean. You mean if we produce fossil fields of 10 to the something Gauss here, how does this link to the 1 Gauss on Gauss and the sun? That was the question. I don't know yet.
But also what about AP stars, my, that naive understanding, I don't know much about this, or that
Yeah.
then we have a collapse, somehow the magnetic field, the thermomagnetic field, like, the dipole field, it's, suppressed convection, so this was not mixed, it's just remain frozen.
But that's
inside
what,
the star,
that's what I would see in
during
the
the
simulation.
star formation. But your idea is that these spots on AP stars were formed, that after the star was formed, there is stability. So there might be some relation of test for this.
Does Günther want to address this question, or didn't understand this?
But listening is time to.
Günther was not listening to the
Why?
question.
Maybe we should say again that this field was frozen from the beginning.
Yeah.
Suppressed convection, star was not fully convective.
Yeah.
Because it's quite strong field, so
That's true, but it's hard to answer. I
it
really can't answer
it
it.
could just happen, some initial conditions to
Yeah.
collapse quickly, and then you suppress convection.
Right.
Is
I
that
mean,
the
this is
observational
essentially-
data? What it is?
It is, no, it's essentially has been simulated in this case.
Günther gives the prize for the best question.
Yes, to Sasha. There's another one for the next talk.
Other questions in the meantime? Before he has his thing up? Before it takes some time. So, any other question in the meantime? No? If not, then let's thank Rainer again, and then we go to the